than E, unless Poisson ratio is equal to 0, okay? But usually that's not the case. All right, so let's continue, and then we'll see a little bit more about this. The second thing is, what is going to be sigma 2,2 or sigma 3,3 in this case? They're going to be the same. But if we multiply these equations, we will see that this is going to be let's do, sorry, I meant sigma 1,1. Sigma 1,1 and sigma 2,2. Let's do sigma 1,1. Sigma 1,1 is going to be this one times that one, which is going to be 0, this one times that one, which is going to be 0, and this one times that one, which is going to be Poisson ratio times E times 1 plus Poisson ratio on the other one times epsilon 3,3. But notice that we already know what is epsilon 3,3, and we can relate it to sigma 3,3. So I'm going to get the sigma 3,3 from the previous equation, and this is going to be 1 minus 2 Poisson ratio, and epsilon 3,3 is going to be 1 minus 2 sigma 3,3. It's going to be that, right? Notice that this one is the same as that one, and the Young modulus appears in numerator and denominator. So finally, we get these equations, which tells me that the effective horizontal stress is going to be equal to the Poisson ratio divided 1 minus Poisson ratio, the effective vertical stress. And that kind of makes sense, right? Because let's come back to the example over here. What this equation is telling me that as I get deeper and deeper, because the solid cannot expand, it tries to expand in the lateral direction, but it can't. Why it can't? Because there is more rock here and more rock here that does not let the rock expand in lateral direction. So if no one can expand, then as a result, you're going to get a stress in that direction. And that stress is proportional to the Poisson ratio. The bigger the Poisson ratio, the larger that stress is going to be. It's like if you go to a party, right? If you go to a party and it's very crowded, you start like to bump into each other, right? Because you cannot move your arms. And it's the same here with the rock. As you get deeper and deeper, then you get more and more lateral stress. How much? Proportional to this, to the Poisson ratio, and proportional to how much vertical stress you have. I have a friend that told me that once he was in a party that was so crowded, that once he got his arms up, he couldn't lower them anymore during the whole party. I don't know if it's right or not, but it might be. Okay, so let's try now to understand the concept of this very important term. And for that, we're going to make a plot. By the way, that coefficient is called the effective stress lateral, or well, actually I should call it lateral effective stress coefficient, or horizontal effective stress coefficient. And I'm going to put the coefficient over here. I'm going to put Poisson ratio over here. We said that the Poisson ratio goes from 0 to 0.5. And now I'd like to see how much this coefficient varies. Okay, so if Poisson ratio is equal to 0, what is the coefficient? 0, right? What about if Poisson ratio is 0.5? What's going to be this coefficient?
1.
It's going to be 1. What is the Poisson ratio of fluids? You could say it's about 0.5. It doesn't really make sense to talk about Poisson ratio of fluids, but you could say that incompressible solids, they have a Poisson ratio equal to 0.5. And that kind of makes sense, right? Because what this equation is telling you is that if your Poisson ratio is high as 0.5, your effective stress, horizontal stress, is going to be the same as your vertical stress. And which goes also into what we have seen before with hydrostatic pore pressure. When you have fluid pressure, the pressure is the same in all directions. And with this equation, we see the same. With Poisson ratio approaches 0.5, then your horizontal stress is going to be almost the same as your vertical stress. But this is not the typical Poisson ratio of rocks. Typical Poisson ratio of rocks is usually lower than 0.25 and more into something closer to 0.1. What is going to be this value if Poisson ratio is 0.25?
1/3.
Very well, 1/3. So it's going to be number somewhere over here. So this is going to be a curve more or less like this. In the case of rocks, the horizontal stress is usually about 1/3 or lower than the vertical effective stress. Whenever we are in a setting there are no tectonic strains. So we're close to the end, and I'll try to do a few more things, but something very important out of here is that you should remember that this is just an approximation, okay? This equation, you have seen it already, and calculating horizontal stress with this equation is the simplest approximation that you could do. Is, for example, if I told you to calculate pore pressure. If I tell you to calculate pore pressure, what can you tell me?
0.433 times height.
Yeah, I'm just going to assume hydrostatic pore pressure. That's an approximation, and in many places it could be correct, but in many other places it will not be correct. And actually it could lead to some serious mistakes. And it's the same with horizontal stress. This is the simplest approximation that you can do. And we're going to see how to compute frag gradient with this. But remember, this is the simplest that you can do. And many times, this is going to be wrong, and you're going to be off by a lot. But it is the simplest you can do. The same with pore pressure. We saw that there can be overpressure, that we can calculate pore pressure in some other ways. And actually, sometimes we have to measure it to get its actual value. With horizontal stress, it's going to be the same. This is going to be the simplest way to calculate it, but there are going to be other ways in order to calculate this horizontal stress more accurately. Yes?
So when you say rocks, are you just referring to the matrix or bulk, basically? Like with
No, not to the rock itself.
just the matrix?
Yeah, everything with pores, with everything in it. Usually, you get the rocks to be over here, and sometimes mud rocks have a little bit of a higher Poisson ratio. And there is a particular rock which has a Poisson ratio that approaches 0.5. And those are salt rocks. Salt rocks cannot take shear stresses. They do, but with time they deform so that stresses equilibrate in all directions. And because of that, that behavior leads to an approximation of Poisson ratio equal to 0.5. Okay, I think I have time for the frag gradient. So let's see if we can get to it before we talk about the general equation for horizontal stresses. Okay, so let's imagine that we need to go to frag a shape. And I have drilled my horizontal well, and I'm ready here to start pumping. I need to know how much pressure I need in order to fracture that reservoir. And I compute vertical stress, and is that I compute pore pressure, and is that, and let's assume in this case that SV is going to be the maximum horizontal stress. And I'm going to make it even simpler. I'm going to say that SH mean is equal to SH max. And I'm just going to call it in this case SH. Okay? All right. So, first thing, the total horizontal stress, as we have seen before, is going to be equal to the effective horizontal stress plus pore pressure. Something that we already know, right? This is effective stress, this is total. The total effective. Okay, so, but now I found an equation for this one, for effective, right? Effective was I'm going to write again here this value for effective stresses, don't be confused. If I use linear elasticity, this is going to be the Poisson ratio 1 minus Poisson ratio sigma v plus pp, right? And but I know how to compute sigma v. Sigma v, if I put it in terms of total vertical stress, which is I know how to calculate, is going to be that. And SH, if I want to compute it with variables SV and PP, is going to be this plus, I'm just doing some math over here. Okay, this is this one plus negative this one plus that one is going to be this PP. And now what I'm going to do, these are absolute values. And if I want to compute the gradient, what do we do? It's not really divide, but you take a derivative, right? So I'm going to write the derivative as delta. Just one more minute, guys. Derivative of SH with respect to Z, this one we're going to assume it constant, is going to be this one, and this one is going to be constant too. Derivative of pore pressure. We know what is this. What is this? We had a name for it. This is the total vertical stress gradient or lithostatic gradient. What is this? This is a pore pressure gradient, may not be hydrostatic gradient. And what is this? And this one now is the frac gradient. That's the minimum horizontal stress that you will need, or minimum pressure you will need to produce a fraction of this.
There shouldn't be a 2 right there, right?
There
One o-
should be a
one-
2, there shouldn't be a 2 right here.
Yeah.
Right? Yes. Okay, all right, guys. I'll see you on Wednesday. Remember that you have a lab, some on Wednesday, some on Thursday, and you should be there. Okay? See you.